You people know that office hours have been extended from whatever it was, 2 to 3.5 now. I'll be in the office from 4:30 till about 8, starting this Monday. And of course, if we need more time, I can easily put in more time. If you have to, I will see you on the weekends. But you have to seriously bring food. Whatever, quality, not quantity. Quantity too, don't bring me a little, If you need more personal attention, kind of more one-on-one time, come later rather than earlier. Close to after, I don't know, 6:30, 6:15, something like that. No, book an appointment tough because it's like 600 people in the course. But you can come in and I'll, kick everybody out and talk to you if we really have to.
Can you actually go slower?
Yeah.
You usually go fast.
Well, if you come in early, I go fast because there's lots of people. I'm trying to get rid of you. Mass production, buddy. Optimization. Okay, so today we will take it a little bit easy. It just dawned on me what we have left to do and how much time we have left to do it. We have lots of time. So we have plenty of time. No. It's never the case that I never fall behind. I can always say, hey, don't cover this, right? No, but we won't do that. We have plenty of time to cover what we need to cover and plenty of time to review. So no worries there. Assignments are all done for the course. They're all posted on EWA. You can do them today if you want, but I don't suggest you do that. Simple harmonic motion and waves are very different. The good news is that we have gone through the solutions manual for those 2 chapters are already posted, 13 and 14. And whatever is posted there is 100%, should be 100%, no errors. Okay, finally caught up to, retaking the initiative on this. And we have suggested problems for chapters 13 and 14. We have no suggested problems in chapter 9, but there is plenty for you to do in the EWA, Enhanced Homicide, and there is no suggested problems in chapter 10 so far. I might put them in this weekend. I might just leave it as is. Chapter 13, we have 3 problems out of the suggested ones that have errors in them. The corrected solutions have been posted for you already, and we're working on, you have the solutions manual is okay for those 2 chapters, for whatever we have selected. Okay. We are looking at 3 more review sessions. One on Wednesday, it's coming Wednesday. One the Wednesday after, and where does that take us? To 11, 12, 13, 20, 27. So we have 3 more of those. Okay. One to wrap up statics and rolling, one to do simple harmonic motion, and one to do waves. And if you've learned anything this term, you would have picked up on the fact that these things tend to feature themselves somehow on the exams. Okay, so if you are paying attention and doing what you're supposed to do, the exam will be divided into 2 parts. Half all of you should get, and half none of you should get. So everybody should be able to get 50, but beyond that, that's it. I'm just kidding, of course. No. Now, the scary business is done, guys. The midterm is gone. Final exam will be more reasonable. You'll be able to write, you'll be able to write a couple of words in there. So back to this, please use energy Use energy and not forces and tension and stuff like that. It's the second law. Use energy considerations alone to derive the acceleration of the sphere up the incline. Assume it's going up. The mass is heavy enough to, so just energy. No forces and stuff. No, just theta. Yeah, you have to do some stuff with it, right? You have to assume motion of some sort. Right? Oh yeah, there is no slipping anywhere. I forgot to say that. No slipping anywhere. So guys, we have two ways we can do this problem, right? We have four ways we could do this problem. Okay, 4 ways to skin a goat. Huh? I don't know. Okay, so the 4 ways for this problem are, well, Newton's second law. You could do it using rotation or rolling as a sum of what? We have 2 approaches for Newton's second law. One considers rolling. It's very important to distinguish between these, are able to work with them, understand the differences between them, because on the final you might want to use one or the other. Bottom line is, remember, whichever approach you use, the one that considers, for example, rolling, remember rolling as a sum of translation of center of mass plus rotation about center of mass. What does that mean? That means some forces equals to ma, and that means some torques about center of mass equals to ICM alpha. So these two are combined. So rolling motion can be considered as it is really a combo of center of mass moving and something spinning on top of that motion. So you have to combine both, because the energy that goes into moving that object, part of it goes into moving the center of mass, and part of it goes into causing the object to rotate. So we have to consider both, because the speed with which a ring will roll on the floor, given kick it like that, is not the same as that of a sphere, not the same as that of a disc. Going downhill, it's also different. So rotation has to play a role. At least, this is a safe bet. If you're not sure about the other approach, we have been calling this approach A so far. And this is, considers, again, rolling to be a combo of translation of center of mass, and superimposed on that is a rotation. And this comes up in the equations of motion you write here. Okay? Some F for translation and some torque for. And the other approach, approach B, says what? Says that in approach B, you don't have to consider translation. In approach B, you consider rolling motion not to be a combo of translation and rotation about center of mass. You consider it, again, translation of center of mass plus rotation about center of mass. That's what we have here. You consider the entire rolling motion to be a series of successive rotations about a fixed point. That fixed point is the momentary pivot. This is called the momentary pivot approach, whereby you consider the point in touch with the ground or the surface that the object is rolling on. You consider that to be your pivot of rotation. And rolling can be considered as a series of rotations about that point. And you can verify to yourself that the physics is the same both ways. If you're not convinced, just use that. But with that, you end up with more unknowns. Okay. The only problem with this is you usually end up with more unknowns. So guys, the point here is that it'll be up to you to choose between A and B. Right? Whatever you want to choose is up to you. What I'm trying to get to is whether you choose A or B is fine, because in the end, even if you end up with more unknowns here, and you have more equations to solve, more work, if you at least write down those equations for us on the final exam, that's between 60 and 80% of your question mark. If they're all correct and proper in terms of the quantities that we gave you without solving them. Okay, we don't want to see that you did not try to solve them. We don't like that. But at least we'll give you lots of part marks if you have the correct form of the solution. That's why, part of why the average is you clue into these things now, and you realize that it's not just the answer that matters to these guys, the actual approach. They're going to grade us on that, and we've done that in the midterm. Now you know for a fact. The other approach says some torques about point B equal to I, careful, B alpha, not ICM, they're different. IB, you have to use the parallel axis theorem. Okay? So this is Newton's second law approach, you do that. What about the energy approach? Same, there is approach A and approach B for the energy as well. And they're both the same. You end up with the same result. So let's say, assume that this guy falls distance h. What I'd like from everybody now is to write down the energy conservation equation for this object that has fallen distance h. Now, how you choose to begin this energy conservation is up to you. You could use work with a non-conservative force equal to change in mechanical energy. You could use work total equal to change in kinetic energy. You have to begin with one of those. Or you could just simply state what you think it is. Energy equals energy and we're done. The only problem with that is if you are wrong, you get 0. Right? With the other approach is, if you write down the law, you make mistakes, we take marks off for the mistakes that you make. But if you give us nothing to work with, then we have nothing to give you. Right? So if you are certain, then put it down. If you're not certain, then walk yourself through it. So 1 minute, please, for everybody. Talk to each other, 2 minutes, fine. Write down that equation, or 3 minutes. You're generous today. Right? Okay, are we done with the energy equation? Do you want me to just write it down or develop it like we expect you to? All right, fine. So I say work with the non-conservative force, one approach is equal to the change in mechanical energy. And then this is not 0 because there is no non-conservative forces doing work. Work of friction no matter. This is, so delta means, so delta K plus delta U is 0. So delta K equals to negative delta U. All right, that's one way we're going to do it. Friction doesn't matter. It's not kinetic, so. All right, guys. So I'm going to erase this stuff here because I need space. Okay, so delta K, help me out, guys. What is delta K? 1/2 m2 v squared plus 1/2 I omega squared for this guy, plus, what happens to that thing there? 1/2 mvcm squared plus, that's the sphere, 1/2 ICM omega squared. If I want to use this approach, that's totally fine. Okay? Now, we will call this sphere, 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 sphere. Okay? Now, that is equal to, this is a change in kinetic energy, delta K, equals to what is negative delta U? If that goes down H, then negative delta U is negative into minus M2GH. What about the sphere? If that goes down H, how much does the sphere center of mass go up by? H what? How much does it go up vertically by? Please pay attention, fill that in. No, M2GH, right? So negative delta U is that, negative delta U. Now, guys, we lose here, here we gain, so that's positive, plus M sphere G times what exactly? Fill that in. People, this moves H. Please pay attention. Kevin, let go of that, whatever. This moves H. This moves how much? H. This moves what? H. This moves H. The top of the wheel moves H. What does the center of the wheel move by? Go back and review the notes on that. If you have an object rolling, the speed of the top is, remember what it was, 2 omega r. Speed of the center is omega r. So if that goes up H, then this will go up what? H over 2. Let's say H is this big. This will be H over 2. And the vertical component for gravity is h over 2 sine theta. So you have to put that in there. So this is h over 2 sine theta. All right, this is the equation. What next, guys? How are these v's related? V and what? Yes. Thank you. Are these omegas the same? No. How do they relate to one another? Radiuses, right? Okay, before we go there though, let's relate the V's. VCM of the sphere and V of the, well, how are they related? How much of VCM is this? If that is the speed of the sphere, VCM, what is the speed of the top? 2. And that is the same as the speed of this guy, V, right? So that, either you multiply this by 2 or you divide this by, I don't know how that works. V is equal to what? VCM times 2, right? So that guy, that V becomes VCM, new line, or should I just muck up this line? All right, so 1/2 into M2. V is the V at the top. This is V, V, that's V, and that's not the same as VCM. Okay, so 1/2 V is 2 VCM, 2 VCM all squared, plus 1/2 I. Let's write it in terms of, guys, what is this omega equal to? I need V in the end, right? What is the omega equal to? Omega is for what? Omega is for the pulley. Omega is V over R, right? Cool? What are we talking about? That is for the pulley. Pulley. Where's the pulley? Pulley is there. That is omega. That is its V. That V is the same as this V, right? So that's fine. But that V is what? Taking it back to VCM because we want only one variable in there. Which variable leaves up to you, but the question is already asking for the speed of the sphere or acceleration of the sphere. Might as well write everything down in terms of the, speed of the center of mass of the sphere. So that is equal to what? To V over R, 2 VCM over R. And what are we doing here? Just so we know, on the side, the V here, that is equal to 2 VCM for the sphere. Okay? So I will put a little sphere on there. Omega then is 2 VCM sphere over R all squared. Okay? Plus 1/2 M sphere V sphere CM squared, that's fine. Plus 1/2, what is the moment of inertia of a sphere about its center of mass? 2/5 M R sphere squared. ICM, right? ICM. Omega sphere squared. One more line, just to make sure we're on the same page. 1/2 into, M2 times 4 VCM squared for the sphere plus 1/2 I times 4 VCM squared over R squared. This is R squared, for the pulley, plus 1/2 M sphere V CM sphere squared plus 1/2 1/5 M. Pay attention here, guys. R sphere omega sphere. What is that going to give me? Omega r is the speed of what? Speed of the center of mass of a rolling object. So that's VCM for the sphere. 1/5 VCM squared. All right, now we have one variable here. We're happy. And that's equal to what? The change in potential energy. Negative of negative is M2GH minus M sphere G H over 2 sine theta. Guys, on the final exam, if you want the full marks for the energy equation, it has to look exactly like this. It has to have given quantities in it and proper moments of inertia plugged in, and otherwise it's anybody's guess. Eh?
Without the answer.
That is fine. If you give me this, that's already 75% of the answer. Yeah. Say again? I don't understand. Sorry, I have no idea what you're talking about. That is it. What this is saying is delta K, change in kinetic energy, because we begin at 0. What is delta K for each object? That's final minus initial for that one. Final minus initial. What is the initial? 0. If it wasn't 0, you have to begin at that point. Yes? Yeah, I'll talk to you about after, because it's not kinetic friction. Okay, it's not taking energy from the, Okay, guys, this is, how do we go from here to using, how do we get A from this? How do you get A from this? Without doing V squared final, V squared initial. What is the cleanest way to do this? I will not do the full solution for you, but guys, you go d by dt of that equals to d by dt of this. All right, so before we do that though, right, we have an issue here. Who caught the issue? We have a problem, and what? What is dH by dt? What's wrong with that? Yes. Guys, we have a problem here, small problem. We haven't hit a problem yet, but there's something that we could easily miss here, right? Please pay attention. First of all, what is d by dt of v squared? I will write it on the side. Please pay attention. This is key to going forward. You're going to do this on your own. You need this piece of, so d of v squared by dt. By the chain rule, what does that give me? Chain rule says it's d of v squared by dv times dv by dt. So that's what? 2va. So that goes in as 2va. Hold on, one at a time. What do you want? Do what? That? That's it. That's all. Guys, it's a chain rule. Who's teaching you calculus? Okay, here. D, please pay attention. How do you do this? dv squared by dt is written as d of v squared by dv times dv by dt. That guy is what? A. And that guy is 2v. So that becomes 2va. All right? Fine. So this is, please pay attention now. You really have to be careful here. There's lots of room for error. You can make a lot of mistakes. What v are we talking about? Cm. What V is this? Cm. What A is that? Cm. Okay? That R will be C. Please pay attention here. On this side. That side is fine. You have the tools to work with it at home. Okay? What about this side? What is D? Please pay attention, guys. What is dH by dt equal to? What is H? The height? The height which the cylinder's mass goes up, center of mass. It's the height that the block moves. So dH by dt is that VCM? No. It is V. And that V is what? 2 VCM. So please keep that in mind. When you do, because that H is the H of this mass. That is twice the H of that guy. Okay? So, yeah. So what happens here basically, guys, this becomes d by dt of H becomes 2 VCM and another 2 VCM here. And then what cancels out? Think with me now. You have that goes in there. It gives you VCM times A, VCM times A, VCM. And here you have VCM, VCM, and the VCMs do what? Cancel out. You scratch them out. Okay? Please finish that at home. Yes, Mark? No. No. Just the speed. Okay. What I would like you to do is please do what I asked you. That I will give you 3 minutes. I don't want to do it, but I'll give you 3 minutes to finish it. And I will write down the final answer for you so you can compare. One of you is going to give me the final answer. Okay, answer anybody? Not yet. What the hell? Okay, I'll do it myself. What? ACM should be, I don't know, what, help, M2G minus M sphere G sine theta divided by the inertia, which is divided by, oh my God, 2M2 2 why? Oh yeah, look at that. Who's the schmuck that said that? You, but I'm trying to eyeball it. I'm not trying to do it. You, maybe in 50 years you'll be able to talk to me. Well, but you have to resurrect me because, you know. Yalla bada. What was that?
You said 50, if he's 18, that would make you 78. 60.
Way to go, Given. That explains a lot of things, man. No, that's fine. Yeah, I'm trying to eyeball it, that's why. I mean, sit down and do it. That's okay, so, and then 2V, I'll try not to make any more mistakes. 4I over R squared. I got that right. Plus, come on, help me, guys. Don't, plus. Just M sphere right now, right? M sphere plus 2 over 5 M sphere. So that ends up being 7 over 5 M sphere. Okay? There you go. Okay. All right. Okay, we do have a mistake. Guys, this is boom. D by dt, 2 VCM, there should be a 2 up there, right? So there's a 2 here and a 2 there. That comes from this 2 here. What? Okay, wait. What are you talking about? What the hell? What? Yeah. Okay, here we go. I did it. Thank you. Took me forever. Of course, you're not going to be given as much time on the final. Okay, so guys, I would like to find the tension that is keeping this beam from falling down. So you have beam, okay, and if we call this, do you know what we call this? Anybody? It's a free hinge. Why do you call it a free hinge? Because if you have no string, that thing will just fall. So now we have tension T. Okay, please focus here. Worry about that later. It's correct. Just do it. I hope it's correct. It's correct. Okay, guys. The beam is more, for all intents and purposes, the beam is uniform. Uniform beam means that the center of mass is where? At the center. So this is the mass of the beam mg, and I have the tension T. And the best thing to do in this case is to sum torques about point O. Sum torques about point O is equal to 0 because we don't want this beam to move. All right, we're going into chapter 10 now. Chapter 10 is on statics, conditions for equilibrium and elasticity. I'm not sure that we're going to cover any elasticity, but at least we'll do conditions of equilibrium. So sum torques about O is equal to 0. Write down the torques about O. What exerts torques about O? I have the torque of mg as a vector plus the torque of the tension equal to 0. Okay? And because this is a vector equation, we need to choose a positive direction. And for torques, remember guys, I told you about 5 lectures ago that we're going to revisit our approach to torques here again. And that is today and over next week. For torques, what is torque? Torque is a generalized force, but basically it gives you an idea about the ability of a force to create rotations. So what is the torque trying to do? Twist. There is a twisting action. You have to be able to see which way it's twisting about the pivot. Okay? It's not that hard. Usually, it's very obvious that mg is trying to spin us this way, while t, what is the pivot there? Right? T is trying to spin us that way. So I will choose one kind of curvy direction to be positive, and that's that. What does that mean now, guys? About the pivot at O. Okay, about the pivot at O. Whatever force is trying to spin us that way has a positive torque, and whatever force has trying to spin us the other way has negative torque. Please keep in mind here, guys, that your choice of direction as up or down is positive, or left or right is positive, has no meaning. Okay, it has no bearing on the problem. For the forces, despite the fact that mg points down or t points up or this way or that way, has no meaning. When it comes to the torque equation, that one, we only look at what is it trying to do. mg by the sign convention is positive. So torque of mg minus torque of T equal to 0. The torque of mg is mg times, what is the torque of mg? It is the moment arm. If you can't find the moment arm, by definition is equal to perpendicular distance times force. So that's one definition of torque. We have three definitions of torque from the beginning of chapter 8. One is what? R F sine theta. Equivalently, we could say R times F perpendicular, or R perpendicular times F. Right? Whatever you want. No, that's Newton's second law. The actual definition of torque is RF. Okay, so torque of mg is distance, which is L over 2 times mg minus the torque of the tension. I will use I have two options, guys. I could either break up T into two components, Tx and Ty. I could do that, or just use the full definition of torque. Okay? For the full definition of torque, I say that this is equal to the whole length, L times T times sine of the angle of 35 degrees. 35 or 37? I got to make up my mind. 35 degrees. Okay? Sine of 35 degrees equal to 0. This means that tension you need is mg over 2 sine 35. Okay? We're not done though. Okay. I want to give you enough tools to be able to start the next assignment if you want to. What I'd like to do next is draw the free body diagram. We haven't done that yet. Okay, this is just eyeballing the problem. I would like to draw the free body diagram of that beam. Okay? Please, we have what so far? We have mg, and we have the tension. What else do we have on the beam? What also acts on the beam? Now, this is where we part ways with scientists and do it the engineering way. Please pay attention, guys. That tension can be broken up into what? Tx and Ty. And that's what you should be doing. Tx, and easy to find. T cos, T sine theta, whatever it is. That is T sine theta, that is T cos theta, that's fine. Okay, guys. What's happening here? That hinge, if that hinge was not there, what would happen to the beam? Imagine with me. If you took out the hinge, that will just fall down. So the hinge must be supporting us with a force that goes up. That's one thing. We must have a reaction force that we call Ry. Now, a rule of thumb is if you know the direction of the force, then go with it. If you don't know, assume a direction. It doesn't matter if you're right or wrong. As a matter of fact, guys, standard engineering practice on a problem with many unknowns, this is easy. We know it has to be up. But if you have no idea, you're looking at a bridge, for example, and you want to isolate the section of the bridge, you have no clue which way the forces are going to act, you don't even bother to waste half a minute trying to guess which way. Because that's a waste of time. It's delaying production for the company. Okay? We don't need to know. We just assume a direction. We assume a direction, and if you're wrong, what comes out in the end? A negative sign. So they don't even bother trying to guess, because if they see you doing that, they'll do something funny to you because you're wasting time. You just sit down, do it, get it done. They understand. Negative means, okay, other way. Okay, so, guys, now what do? Sum of the forces, we have three conditions of equilibrium on any object. Sum torques equal to 0, sum Fx equals 0, and sum Fy equals 0. Torques about what? Please pay attention here. Torques about what? Any point in space. What does that mean? I summed the torques to get tension about O. I could have also done some torques about that point. I could have some torques about that point. That beam is not rotating, is it? Whatever you sum the torques about has to be valid. It's okay, has to be zero. If the beam is not rotating, I could sum torques about. Typically, we don't go sum torques about here. Why? Because that will leave us with too many unknowns. Okay? We sum torques about there or there, whatever suits us. But these conditions about some point P, any point. Okay? Now, sum of the forces in the y direction equal to 0. This means that Ry plus mg plus ty equal to 0. Right? I'm taking another minute. We pick up to be positive, then Ry minus mg plus ty equal to 0. What is ty equal to? Ty is t sine 35. So what becomes of that? Ry equals to mg minus t sine 35. What is t sine 35 equal to from there? So it's equal to mg minus mg over 2, and Ry is mg over 2, because t is mg over 2 sine 35. Third equation. Now we go here. We have a problem. What's the problem? Sum fx on the beam equal to fx equal to 0. Therefore, look at this, guys. You have tx plus what equal to 0? That beam is being, if this wall was made of putty, some sort of Play-Doh, what would the beam do to it? It will sink in. So that wall or that support is providing a force out that's keeping the beam. If the wall was not there, then that beam will go in, right? So the wall is pushing the beam out with a force. Again, if you don't know, you assume, but now we know. We call this Rx or Ax or whatever. So Tx as a vector plus Rx as a vector equal to 0. I will pick this to be positive. Then I will have minus Tx plus Rx equal to 0. Rx is equal to Tx, which is equal to T cos theta, which is equal to mg over 2 tan theta. Okay, guys? What does statics involve? We give you a problem like this and we say simply one word: find all the unknown forces. Okay? It doesn't say tension, it doesn't say all the unknown forces on the system. Okay. Have a good weekend.